in the string. Who has an idea about how to make a push-down machine that does that? How would you do it? Give me a plan. Give me a man, a plan, a canal.
You can,
Yeah, Chris, go ahead.
well, you can have a stack that keeps track of your surfeits and deficits, and you can randomly throw zeros and ones in and move your stack up and down accordingly, but you can only quit when your stack's empty.
Okay, so the stack goes up when you see a 0 and goes down when you see a 1. What if it gets empty?
Then fill it up with one surfeit symbols.
Okay, what if it gets empty and the next symbol is a 0?
Well, then you throw in a zero surfeit.
Okay, so when it's empty, I have to look at the next symbol, and if it's 0, then I go into a place where I push zeros on, and then when I see 1s, I pop them. And if it's 1s, I push 1s on. When I see 0s, I pop them. If it gets empty again, I can start again. And then I accept whenever I get to the end of the string and the stack is empty. That's completely reasonable. And on the homework, I asked you to do this deterministically. How do you do this deterministically? Let's take your strategy and kind of write it up. At some point, there's going to be a state, and on this state, if you see a 0 and there's a 1 on the stack, then you pop it, right?
Yeah.
And then at some point, you see empty, empty stack, empty, and you accept, right? Something like that. What else do you have here? What happens if you see an empty stack here? And there's a 0 on the 0, empty stack. What do? You're going to push the 0, right? Look at these two choices. How do you know which one of these to take? In other words, what if I'm reading through the string and the 0s and 1s equalize after some amount of symbols?
Then we need to have something coming out of the accept state.
Yeah.
Instead of having to just fall off the end if there are more symbols. If we find more symbols in our string,
We just go back into the game.
Yeah, but it's already non-deterministic.
But it's non-deterministic,
What is it?
right? Because at this point, I don't know whether to stop and say I'm done. And in fact, let's say they equaled out after 3/4 of the way through the string. Couldn't I just not read another symbol and say I accept? Well, I guess then you would die. That's no good. And if you want to come back, you can come back and fix it. But at this point, you have a choice. Do I continue looking at symbols, or do I stop and accept? And there's no way to know if the string is over yet, unless you look ahead at the next string. So technically, there's no way to do this deterministically. Technically, you're really stuck with non-determinism here, even though you should get a gut instinct that this isn't particularly non-deterministic. I just can't look at the next symbol, and I'd like to see if I'm done yet. So my solution, the actual solution to this is very technical and annoying, and it has to do with these Lrk grammars. This is not an LR0 grammar. An LR0 means you don't have to look ahead at all. This is an LR1 grammar. It's deterministic, but you got to be able to look one symbol ahead to see if you're really done. Right? So you get one little extra look ahead. I want to look ahead to see if there's something there. If there's something there, I know to do this. And if there's nothing there at the end, if it's really empty, I'll go do this. Then it's no longer non-deterministic, but I need to look a symbol ahead to make it deterministic. That's the distinction between LR0 and LR1. This is an LR1 grammar, but not an LR0 language. So you asked the question, and you opened up Pandora's box. The way that I tell people to handle this, because usually we don't spend 3 or 4 lectures talking about Lrk grammars, as interesting and as difficult as they are, we don't spend time on it. So what I tell people to do is in these situations, you can always assume that at the end of your string is a special symbol, like a pound sign. Right? And that will end every input string. And that way, instead of the E here, you have a pound sign. And now it's deterministic again. And what this basically does is take away the whole issue of having to deal with deterministic things that seem like they have to be non-deterministic, but really they're deterministic, and let's make a whole theory about how to show they're still deterministic. Let's just chuck a symbol on the end and not deal with it. Right? So if you ever have this difficulty and you think you can do a deterministic one, and the only thing that's in your way is looking at the end, then imagine there's a special symbol at the end. I mentioned this once at the very beginning when we talked about grammars, and it's coming up here. So you can do this if it makes it convenient for you. That's the upshot.
So
So if you want to know the end of a string, you really don't have to look ahead, basically. You don't need a look ahead grammar to know just that the string is ending.
Right, right. And there's a theorem that says that LR0 grammars are the same as the deterministic context-free grammars, context-free languages that have the prefix property. In other words, if you put a special symbol on the end, there's no prefix that could possibly be part of that language. So if you take any language that's deterministic and put something on the end of it, those are the LR0 grammars. In other words, if I put this pound sign here, then I can get all the LR0 grammars. If you get this, fine, and I don't see how you really could with just a brief explanation like this, but you get a little flavor of what these Lrk grammars are like. We're still hoping to spend some time on this in recitations. It'll be an advanced topic, and it won't be part of the main course, but hopefully we'll get time to do it. All right, so...
Just in that
Yeah.
machine there, you
Yeah.
start with a 1, and the stack is empty.
All right, we'd also push the 1 on, I guess.
Push the 1 out,
Yeah.
and then
So if there's 1s on the stack, we might need 2 different states here. If you start with a 1, go to a state that pushes 1s and pops 0s. If you start with a 0, yeah. Yeah, I didn't write the whole machine down. But you're right, Neil. It needs a little bit of thought. Yeah. We did this 2 months ago. Or 3 months ago. We did this in algorithms when we talked about dynamic programming. And I know what you're thinking, oh gee, but I don't remember that. Don't build on what we did then. I'm not. I'm going to do it from scratch. I'm going to pretend you never saw it. And I'm going to pretend that if you did see it, you never understood it. And that if you thought you did understand it, that you were wrong and you really didn't understand it. All right. Now everybody's got to be willing to listen. Now that we're on the right path. This is an algorithm named for the 3 people that worked on it independently. Koch, Younger, and Cassimi, I think are their names. And they came up with an algorithm for parsing that takes a context-free grammar, takes a string, tells you whether that string can be generated by the context-free grammar. Their algorithm runs in order n cubed time. And that's a very important result because it takes it out of the exponential time algorithm that we got from Chomsky normal form. Chomsky normal form, remember, has 2n minus 1 production steps to get a string. So 2 to the 2 to the n minus 1 is the size of the trees. And that's the worst case for finding whether a string is generated or not. Just generate all the trees. We want to do better than 2 to the 2n minus 1 of Chomsky normal form brute force method. And this is a lot better. This is polynomial. And the idea of this is dynamic programming. We think of kind of a recursive idea and notice that the subproblems are being computed many, many times. Keep track of each subproblem once, and we'll get the answer to whether a given string is generated by a given grammar. It's a dynamic programming style algorithm. Dynamic programming. And I'm going to show you all the details about this and do a particular example. But before I do, I want to just mention that this is not used practically for any kind of parsing nowadays, because there are better polynomial time algorithms than this. What's more, this algorithm works for any context-free grammar. It doesn't have to be Lrk. It doesn't have to be deterministic. Any real grammars that work for programming languages are Lrk grammars or LLK grammars. They are deterministic. And therefore, you can probably implement them more quickly and more easily. This is just completely general and shows you that it is possible to do parsing even for non-deterministic machines in polynomial time. The real fast algorithms that work with Lrk parsers are linear time, and in practice even, in real time, maybe faster by a constant factor. I mean, very, very quick. They basically compile your code by looking at it in one pass. All right. So with all that as intro, let's go ahead and write an example grammar up, and I'll show you how we're going to go ahead and make a table and figure out whether this grammar generates a given string. Here's the example grammar. Again, as the last few examples we've had, it's very useful to have this in Chomsky normal form. It makes the description of the algorithm very concise and without a lot of exceptions. So there's the grammar, and here's our candidate string. I'll put it up here. 1, 1, 0, 1, 0, 0.